What the heck?
Hectagon.
Hello. This is the first new video in a long time. I'm looking a little shaggy. I need a haircut. I need a shave. I'm wearing the same shirt as the last video, but I promise it's been washed in the last month and a half.
Monday Math Nuggets.
Yeah. It's 3 p.m. and I'm drinking coffee. So today we're going to explore a lovely little geometric fact that I'd love to prove. We're going to do the inscribed angle theorem. And in the next video we're going to do multiple proofs that show that the sum of all the angles inside of a triangle are equal to pi, right? You add up all the angles and you get 180 degrees or pi radians, and we're going to prove that too. And I may use that as a tiny little generalization volley at our good boy Papa Flamdam. So let's get right to it. Let's inscribe some angles. Okay, so we're going to prove the inscribed angle theorem today. And it's a very lovely, simple fact. It just says that if you have a circle and a central angle in that circle that subtends some arc, we'll call it theta. So if this is radius, I guess it doesn't matter that this is radius r. I guess we don't need that. It's actually irrelevant what the radius of the circle is. If we now pick any point from here to here along this major arc and have it subtend the same angle from that point, so this is the new vertex of the angle, and simply connect it to the same 2 points, this will always be theta over 2. Which is very nice. It's not an obvious fact that that's true, but if you let this vary, this angle will not change. These lines will follow the point, and even tucked in here, connected like that, that angle will still be theta over 2. And so I'm going to prove this fact today, and it's any angle in here. As it turns out, the opposite sort of fact is if you pick an angle anywhere on the minor arc and connect it to the same 2 points, you actually get half of this reflex angle right here. So it's always half of the angle on the other side of the central angle. So if the point's over here, it's going to be half of this part. If the point's over here, it's going to be half of this part. So it's actually always true no matter which side you pick. It's just true for the opposite side of the angle. So we're going to prove this, which will prove both of them, because there's no reason for reflex angles to be treated any differently than acute angles. Or right angles for that matter. So let's just set off to prove this fact now. So we actually have to prove it in stages. We have to do 3 different things and they will simply build off of each other. So I'm going to pick a new color. We're going to do this nice orange. Start with a central angle, some central angle inside the circle. And then we have to do it case by case. So the first case we're going to do is when the inscribed angle that we pick has a ray that lands on the ray of the central angle as well. So one of the rays of the inscribed angle is actually a diameter of the circle. So we know that this is theta, and we want to prove that this is theta over 2. Well, in this video I'm going to assume that the angles inside of a triangle are add up to pi radians. So this must be pi minus theta because this is a straight line. So they must add up to pi radians, right? If we take this away from pi radians being the sum inside of a circle, right, we have pi minus theta. That means that the last 2 angles in this triangle have to add up to whatever this is, which is pi is 0, minus theta is positive theta. So both of these angles have to add up to theta. But we also know that because all of these are radius lengths of the circle, by the isosceles triangle theorem, the opposite angles to congruent sides in a triangle must also be the same. So because these 2 angles are the same and add up to theta, they must both be theta over 2, which means in particular that this angle is theta over 2, which proves this one single case of the inscribed angle theorem, right? So that proves that, right? If this is theta, then this must be theta over 2. And now we're going to use this to prove it for another case. So what we're going to do is we're going to keep the same angle, but remember this in theory could be any theta, right? This could be any central angle at all. And now instead of picking one that lies on one of the rays, we're going to pick one that straddles both of them. So we're going to put this one here, and we're just going to do that. right? And we want to prove that this angle is theta over 2. As it turns out, we can just break theta up into theta 1 and theta 2. And now we've actually broken, so we know that theta 1 plus theta 2 equals theta, right? So that's what we're saying. But we've actually just broken up this case into two of the cases that we already proved. So we know that this has to be theta 1 over 2, right? The first theta over 2. This one has to be, this one right here has to be theta 2 over 2. And if we add theta 1 over 2 plus theta 2 over 2, we get theta 1 plus theta 2 over 2, which has to be theta over 2, the original central angle, which is the entire central angle here, right? So that proves it for two of the cases, and now we have one more case to prove. All we have to do is prove the case where instead of lying on one of the rays or being around both of them, it's actually off to the side, and that will prove it for every single case. So again, we're going to start with some angle theta. We're going to pick a point over here now, such that we get this sort of thing right here. So we want to prove that this is theta over 2, right? That's what we want to prove. So what we're going to do is we're going to actually give ourselves another auxiliary line like so, because what that allows us to do is it allows us to call this whole thing theta 1, and this little one right here, theta 2. So in this instance, it's not theta 1 plus theta 2 that gives us theta, it's theta 1 minus theta 2, because it's this whole thing minus this right here, right? And we know, therefore, this whole thing must be theta 1 over 2, because it sort of inscribes this entire thing that theta 1 does as a central angle. So this must be theta 1 over 2. And because this does the same thing with theta 2, this little one in here must be theta 2 over 2. So in this case now, we have theta 1 over 2 minus theta over 2 is going to give us just this angle right here, right? So we get a minus there and a minus there. But we already know that in this instance, theta 1 minus theta 2 is theta. So this, again, gives us theta over 2, which proves it for all cases, right? That's every single possible case you could get, sort of in the most general sense, and that proves the inscribed angle theorem. So that's been our Monday Math Nuggets. I think I'll share one more thing. So this is actually just this fact is actually just a special case of a more general fact. And that more general fact is this fact, that if you have two intersecting chords in a circle, then this angle theta, and we'll call this arc length, if we consider this from the center as a central angle, we'll call this alpha, right? This is alpha right here, this thing right here, and we'll call the central angle of this beta, the central angle that subtends that arc, whatever it is. It actually turns out that alpha plus beta over 2 is equal to theta. Theta is the average of these two quantities, alpha and beta, right? And that becomes the inscribed angle theorem as this point moves towards the circumference, because then beta goes to 0, right? And then we end up with alpha being the central angle of only one point, because this migrates towards the circumference, and then beta goes to 0. So then theta just becomes alpha over 2. But alpha then is the only arc, and so it's just the average. The average of something in 0 is just half of that first thing. So that's how it's sort of a special case of this more general fact. I don't actually know what this one is called, but you know, it's a more general statement. So thank you for joining me for this Monday Math Nuggets. I hope it was nice. In the next one, we'll be doing a bunch of different proofs that the sum of the three angles inside of a triangle is always pi radians. And so I had to use that fact to prove this, which means that fact implies this. And in one of my proofs, I'm going to have to use this fact to prove that the triangles always have 180 degrees in them. So it's a bijection, I guess you would, not a bijection, a biconditional statement. One implies the other, if you will. So in the next Monday Math Nuggets, we'll be doing that. So thank you very much for watching. Bye-bye.
Ooh, you're a cool cat, tapping on a toe, you new hat. Ooh, just cruising, driving along like the swing kid, feeling the beat of my heart, yeah. Ooh, feeling the beat of my heart.